let's start off from last night, understanding that if we start with a parent graph of f of x equals absolute value of x, and then we can make it a little bit darker so you know it's an absolute value and not in 1. If we know what this looks like, right, that just looks like this, v. If we start adding, subtracting some numbers to this, it's really just moving this graph around. It's not a different graph, it's just moving this around. So what would this, plus 1, what does that do to the graph? It would shift it where, what direction? On the outside, it'll shift it up. So when it's on the outside, when it's on the outside, it shifts up and down. So if it's like a -1, it would shift down. When it's on the outside of the absolute value. If it's on the inside, like -2, which direction would that shift? Now that's where it's deceiving. You think it's -2 would be to the left, but it's really to the right. So understanding this idea, this works for basically every graph. It works for parabolas. We kind of looked at parabolas yesterday. X squared, y equals x squared. It looks like this. Right? Y equals x squared minus 1. It looks like this. It just moves everything down. So it doesn't matter if it's absolute value, a parabola, or even a straight line. If you had y equals 3x plus 5, y equals 3x. There's y equals 3x. Y equals 3x plus 5. If you add just a plus 5, like we're adding here to plus 1, it just moves this graph up 5. So it's the same thing, regardless of what type of graph we're dealing with. This on the outside, this shifts it up and down. And this part on the inside is the new part, where, yeah, it says -2, but it really shifts the other direction. Why is that? Because when you plug in +2, you get to 0. 2 minus 2 is 0. So that's why we're going to start at +2. So this graph right here would be just like this, just a V, but it's going to shift up 1 and then right 2. So that one would just start just like that. And we wouldn't have to go through this whole process. Okay, x and f of x, let's plug in numbers and find out what we don't have to do anything. We know because of the bigger picture, this parent graph, it's just being moved around. It's being moved around. So we're going to use this idea for these new types of graphs today. Okay? They're called step functions, or another name for it is greatest integer function, and then also piecewise. So it's two separate types of graphs. Step functions are going to be very new. Piecewise functions is going to be like blending or combining some stuff we've already learned just into one file. So let's take a look at the stepwise functions first, piecewise functions last. So last night I think we looked at what? Absolute value, constant, linear. So we did like 3 types of graphs. Yesterday we did 2 today. Once again, it's worth repeating. Remember our parent graph, which looks like our parent graph looks like this. Right there. This is f of x equal to absolute value of x, right? So what happens if, what is the equation of this graph right here? The same one, but it's moved where? So it's going to be absolute value of x, and then the plus 1 on the outside. down here, what would be the equation of this one? -2. Very good. So it's the same graph, it just moved down 2. Just for kicks, review. What would what if we went this direction? What would that be? To move 1 to the left. 1 to the left. Now this is where it's on the inside. Is it plus or minus though?
Minus.
Plus. Remember, it's a different sign when it's on the left and right. Because if you plug in -1, that's when you get 0. So if I plug in -1, that's where we're at. This is -1, and we get 0. So it's the opposite sign here. But notice when it's on the outside, it's normal. Plus is up, and negative is down. And then likewise, if we did this, over here, this right here, let's move 1 to the right, then it's going to be, it's going to be the -1. It's opposite with the left and the right. Because if you plug in +1, if you plug in, that's how we get 0. You plug in +1. But up and down, it's like normal. Ooh, this will help us a lot because it doesn't matter if it's absolute value, x squared, or regular, it's all the same thing. All the same thing. All right. Any clarifications needed here? If you want to, here's where you start taking good notes. Notes means writing down things that are going to help you later. Does that mean it has to be written down for you? No. So something like somebody mentioned, oh, so it's opposite when it's left and right. That'd be a good note to write down. Oh yeah, +1 starts at -1. -1 starts at +1. Good thing to write it down. That's taking notes. Anything you might need for later, not just copying down. Okay, here we go. Read that to yourself. And let's think about how you would go about graphing something like that. This is the big idea. If we understand this, we understand the whole homework. All right, what do we think? $5 for every full box of newspaper, but you don't get any money for a half box or 1.5 boxes. You don't get more money. There you get $5 for the first one. As soon as you get 2 boxes, then you get $10. So is it possible to get like $7.50 here? No. No. It's impossible to get $7.50. So let's think about this. For one. Well, let's actually start with this. For 0.5, how much do you get for half a box? Nothing. 0.75, how much do you get for that?
0.
0. 1 box, we get 5. 1.5 boxes. You get 5. You still get $5. You got 1 full box. And then finally, like a 1.99. How much do you get?
5.
5. Yeah. So 5. 2. And we get 10. So we're just making a T-chart, right? That's what we're doing. Oh, good way to start, right? So we have our boxes, B, and our dollars, for B. How much money we get? And so, it's impossible to have negative boxes, right? We can't have a negative box, so we're not going to be graphing anything negative here. And for this problem, we can't have negative dollars. So this is going to be entirely first quadrant, both numbers positive. But we can extend this to have negatives in the next part. So same thing here. 2.75 boxes, still get 10. Finally, we get 3 boxes. So we're making big money now. Carry 3 boxes of newspaper. So let's go ahead and graph this idea. Let's see how it comes out. I'm going to make this 1 box, 2 boxes, 3 boxes, 4 boxes. I'm going to say this is $5, $10, $15, and so on. So you can always make your scale what you need. You notice I'm counting by 2 squares here, counting by 5s here, that's fine. Make sure you're consistent. Okay. Alright, so let's just plot these points. Let's see what comes out. So for right here, if I have 5, well, first of all, if I have no boxes, yeah, I have no money. If I have half a box, here's a half. Half is right here, right? This one half right here. I still have no money, 0. What happens? What about 0.75? I still have 0. What about all these decimals right here? What are they? 0. Yeah, they're all 0. So I have a bunch of points. So when, over time, as we keep on doing this, it just becomes solid. Now what happens at 1?
You get $5.
Now we get $5. So we get to 1. Where should I put the point?
5.
Yeah, right at the top. And then the same idea. Repeat. Okay, if I have 1.5 boxes, I still get $5. So I still have 1.99 boxes, still have $5. And so same with all these points right here. So 2. What happens here at 2? Jumps. Or in other words, saying it steps up. Hence the step function. Everything here, 2 point anything. And then what happens when I get to 3?
$15.
Goes to 15. It steps up again. So you can see this pattern continues. You see how it kind of steps up?
Stairs.
Yeah, going up steps. So it's called the greatest integer function, also called the step function, because we have those steps. There's those steps. Another thing worth noting here is that we have to do an open circle here. Because we have to show that, yeah, 1.99, but not, 0.99, but not 1 is an answer. Same thing here. We have to put open circles at the end of each of these. Because they jump up. At that point at 3, it stops being on here. So you stop getting $10 and start getting $15 right at 3. But 2.99 right next to it, you still get only $10. We're going to put these open circles up here. So this is the step function. And this is what you're going to be doing, creating step functions. So let's extrapolate to something a little more abstract and look at some notation. So first of all, this is the notation for a step function. See how it's basically like a double bracket? That means step function. Not to be confused with absolute values. So as we're doing these, as always, you have to be able to distinguish between is this step function or is this absolute value. So just know this means step function, which is also called the greatest integer function. Two symbols. Very algebra 2-ish. We're doing so much algebra 1 review, now we finally get some new stuff. Now, most of what you're going to be learning on this is conceptual. It's not going to be about, okay, how do you do it? You still have a T-chart. You still have all the basic things you already know to do. It's just the graph looks a little different. That's all. More conceptual. All right, let's reverse real fast, though. Look at this. How would you graph this? What would it look like if this was absolute value? What would that look like? What does this plus 1 do to the graph?
Makes it go left.
Makes it go left, right? So reverse real fast. Yeah. Right here, remember? When you add the plus 1 inside, it makes it move to the left. Same thing here. Same exact thing here. If we look at this, if we know what it looks like without the plus 1, it's going to be the exact same thing, but the whole graph moves to the left. So I'm just going to pull up a snapshot of from your book on page 95, right here, page 95. This is what just the regular old step function of x looks like, the greatest integer of x. You can see how it just goes upstairs, it just steps up. This is our parent function. Notice how we have the closed circles, because that's where it jumps, you know, from here, this is where we start making more money from 2 boxes, from $5 to $10, and we have those open circles. Another reason we need one closed and one open is because we need to keep this a function. If these were both closed, then x would be repeating, and we would not have a function anymore. Remember, if the x's repeat, yes, the x's repeat, no, it's not a function. So we need one open and one closed, so it continues to be an actual function. Okay. So, based upon what you guys did last night, you know, well, if I know what this looks like, okay, this graph right here is the same exact thing, just everything's moved to the left one. And that'd be correct. That'd be absolutely correct. So we're going to use what we learned from before and apply it here. Now we're still going to verify it now with a T-chart, just for old time's sake. Not something we're going to do all the time, every time, but for now, yes. So if we plug in, pick some nice numbers, I don't know, -3, -2, some negatives, some positives, 0 always, 1, 2, and 3. We pick some numbers here. Let's see how to plug them in. And later on, I'm going to show you a certain strategy to picking some nice numbers here so things don't go off the wall. We're going to plug it in like we always do. I'm going to plug in, start with 0, why not? Plug in 0, 0 plus 1 is 1. I'm going to put that in there. And then I'm going to plug in 1. 1 plus 1 is 2. Yeah, so nothing different from what we already know. 2 plus 1 is 2. What does this mean? Basically, from 0 to 1, our answer is 1. So from 0 to 1, here to here, here's x equals 0, here's x equals 1. My answer is going to be 1. Right here. Starting here to here. There we go. 0 to 1, my answer is 1. So basically, another way of looking at this is 0 point anything, 0.2, 0.3, 0.75, 0 point anything, you get 1. 0 point anything, you get 1. So about if you have 1, what happens at 1? 1 is where it jumps, so 1 is equal to 2. 1 is where it jumps. And then 1 point anything. 1 point anything. 1.75 boxes. Doesn't matter. 1.5 boxes. It all gets you the same thing. 2. 1. About 2 right now. So all my answers are 2. Yeah. And then now from here you can kind of infer, after you do a few of these, there's a pattern to the graph. And just continue it on like this. all this. And also work our way backwards. So look at our pattern here. 4, 3, 2, 1. What comes next? 0. Just continue the graphs. Continue the graph. Make sure you have those solved and open circles correct. That's your step function. Set to catch up on something. It doesn't matter. 1 point anything. It doesn't matter. 1 point anything. 1, 2. 1 point anything. It doesn't matter. The answer is always 2. The answer 2. Either way. That's why it's 2. Now, how do you link this to what we already know? What would be a good thing to do? Alright, what if this was the equation right here? What if this is just f of x equals x plus 1? How would you graph that? Yeah, plot the points. What's the slope here? 1 over 1. Yeah. Y-intercept is 1, and you go up 1 over 1, right? So let's do it. Right here, y-intercept is 1, up 1 over 1. There's a dot. Up 1 over 1. There's a dot. So you can see the dots in our step graph are the same as if we just graphed this as a regular old y equals mx plus b slope and y-intercept. The solid dots are identical. Okay, so if you get stuck or you're in a kind of jam and you don't like these funky new brackets and things like that, take them off and just do the dots. But don't draw the straight line through. You'll have half your graph as long as you can. And instead of having everything connected, if these are connected, it'd be like we have fraction answers, but we don't. We don't. You don't get more money. You don't get $5 or something. This goes to 5, it jumps to 10. With a linear equation, a straight line, we wouldn't. All right, our fun part. What is domain and range? Okay. What is domain and range? Remember, domain is kind of linked with our x's. What are we allowed to plug in? Yeah, we can plug in any number. Good, that's got that quick. Done that quite well. Yeah, because remember, even though we only have integers right here, remember right here, it's 1 point anything. We can plug in 1 point anything. We can plug in 2 point anything. We can plug any decimal fraction that we want. However, what about the range? Our answers. Can we get fraction answers? Can we get decimal answers? No. If you look on the graph, if you look between any of these two lines, you see that there's no red. Our graph doesn't go through it. Our answers are only on these numbers. What's the name for these types of numbers that are exactly on where two of these black lines cross? What's that? What is it? Yeah, when there's no fractions and no decimals allowed, what is that called? Wholes. Now whole numbers are what? 0, 1, 2, 3, 4. Can we have negatives here? Yeah, we have negative. Yeah, here's negative 2. Here's negative 3. So we have negative 2, negative 3, 0, 1, 2, 3, 4. Oh yeah. We have the integers. Our range is the integers. Alright. And think of it, range, possible answers. Possible answers. Look at all our answers. They're only integers. There's no way to get a decimal in there, no matter what. There's 1.75 boxes, still get you $5. 1.5 boxes, still get you $5. See how the answer is always $5. Never, oh, 1.5 box, that's $7.50. No. It's 1.5 box, $5 no matter what. We're not going to budge from $5 no matter what. Our answers are always going to be $5 5, 10, 15, 20 for that original problem. But for this, just a regular old step function, the answers have to be 1, 2, 3, 4, 0, -1, -2, no matter what. Can't get away from it. All right. Any clarifications needed so far? Feeling? Give your brain a little break. In general, with steps while you're thinking of your questions, okay. Consider the behavior of the graph, which means what does this do? What does the +1 on the inside and the -1 on the inside do? Use a table. Okay. Look at whole numbers that are less than or equal to x, so that just means consider positive zeros and negatives, everything. Look at everything, not just the positives and see what happens there. And of course, do your domain and range. But in general, the domain is always all real, so we can plug in just about anything we want. It's just that our answers are limited. Just like on our graphs before, all our answers for some of those absolute values were all above 3 or all above -3. We couldn't have anything below. Let's look at another, but this time let's be a little more wise about it. Now we know. What will this graph look like compared to our original graph? Compared to this, original, just good old step function, no pluses and minuses. What will this graph, how will this graph move? To the right 3. Yeah. So, you can see right here how it starts at 0. Where's it going to start instead? It's going to start at 3. Go over. So, we can start here. That's going to move to the right 3. 1, 2, 3. So we're going to start here. Solid, open. And then it's going to step up. Solid, open. Solid, open. Yeah.
Is there only going to be like one?
No. No. It will change. We're just sticking to the basics now. Next slide, we'll step it up. And then, of course, it's kind of like rise over run. Notice how, once again, if we didn't have this, step function right here, what would the slope be? Maybe 1 over 1, right? We'd be starting at -3. And we'd be going, okay, up 1 over 1, up 1 over 1. You could also go down and left, but with the step function, instead of connecting all these like this, the graph goes straight. So use a linear equation to help with this. Let's go. Well, if it lines up, you're fine. So these little basic ones like this works just great. You know, we're just moving it just to the left, just to the right. It's nice. Yeah. Question?
Will they ever go backwards?
They ever go backwards. So like, will the steps be going like this?
Yeah.
Yes, they will. What line would go like this? Yeah, like a negative slope, right? So if I had like -x plus 1, that would be like right here. That'd be like right here, and it'd be going down. So the steps will be going down if there's a negative. So for you guys, it would look like this. So right here, that would be an example of going down with a negative on the outside. See, so we have a negative. Say it again? Building dots will be going down like this. Yeah, we'll look at that in a second. Actually, I think we have one on the homework. I can bring it up real fast. Well, here's the thing. You have to make a table when you need to make a table. So sometimes the basic one is really to the point. Like here's one we just went over. X plus 3. This is just the solutions for your homework tonight. Just move to the left 3 times. And we'll get to, here's move to the right. So, 2 times. Now here you can see, I 2's on the outside, you see how it kind of jumps too. So they can jump a little different. They don't have to be every single one. And we'll talk about these in depth in a second. Here's a -3. Now you can see it's like a negative slope. It's going down. Notice how the dots are still on the left. Dots are still on the left. Opens are still on the right. So this is 0.8. Oh, just a plus 3 on the outside? No, just the same old thing, just move to 3. So instead of starting here, it starts at the left. So yeah, these parent graphs are very useful. We'll get to those in a second. Again, here's a -x. Notice how it goes down. Now there's a bunch of other ways of looking at using all this. I'm not showing you this. It's okay. You'll be fine. So we can look at this at another time. We'll get into the nitty-gritty about what this all means. So we're almost done. Alright. If we're going to graph this, now how would that look? What would that look like? So first of all, I want to make sure, since we're talking about integers, I want to make sure that my answers are integers. It helps out an awful lot, just like on these previous problems here, or these previous problems when we did this. These are integers. They're counting by 1. We need that to happen. So we got to think about what numbers can we plug in here so that we get integer answers and we can't skip them. What do you think? Plug in 2, what happens? Decimal. Yeah, decimal. 3 would be a good one. Yeah. 6, 9, 0. Yeah, let's not forget that. -3. Yeah. So there's some. We don't want to just pick things at random. Let's pick something that we can use. Alright. Plug in 0, what do we get? 0 divided by 3 is 0. Plug in 3, what do we get? 1. And plug in 6, what do we get? 2. Now let's read this carefully. This is a good time to pay attention. So from 0 all the way to 3. My answer is going to be 0. So from this x to this x, from 0 all the way to 3. Because notice how only when I get to 3 does it jump up. Okay, the next one is 3. That's where it jumps up. So see how this takes up 3 squares? We're counting by 3's now, as opposed to just 1, 1, 1. Then it jumps up, and then once again at 6, that's when it jumps up again. 6, it jumps up to 2. That's when it jumps up to 3. Kind of go off the graph here. And likewise, we can go backwards. You can see the pattern here. Okay, 2, 1, 0. We get -1, -2. So we get the same thing. -3 to -1. 1, 5. Then it jumps up. At 0, that's when it jumps up. -1. So yeah, we can get some different graphs. Okay? Still, how can I have another way of getting these points? How do I know where those are? Yeah, let's look at this. How would you graph that? What is that? We usually don't graph it in that form. X is the same as 1x. So that's the same as 1/3 x. Rise over run. What's the y-intercept? 0. Yeah, there's no number here, right? So y, how do you graph 1/3 x plus 0? And here's 0. Up 1 over 3. There it is. Up 1 over 3. There it is. You can also go down and left. Down, left. There it is. So if we get confused from the very beginning, I don't know what all this stuff is, just take off those weird looking brackets, graph the dots, don't connect them though. If you have the dots, you're halfway there. All right. Domain again, all reals. That's R for all reals. Range, once again, integers. Only the integers. We get positive answers, we get negative answers, but there's no decimals or fractions as our answers. Last one, and we'll be done. Again, I want you to think about this right here. How can we get numbers that are consecutive integers, that are in order? Consecutive just means you're in order. 1, 2, you don't skip them. How would we do that here? We're just going to plug in 0. Plug in 0, you get
0.
0. But my next number I want to be over here is 1. Then I want to have a 2. What do I have to plug in to get those numbers? What do I have to plug in to get 2?
1.
1. What do I have to plug in to get 1?
A half.
Half. So I'm choosing the numbers x. I already know my answers. They have to be this. That's what I'm starting with. I'm starting with this. And then I'm figuring out, well, what x's do I need in order to reach 1, 2, negative 1, negative 2. Okay? What does this do to the graph? All right. So from 0, 0, there we go. Where's the jump going to happen? At half. At 1 half, I'm going to jump to 1. So right here, I'm going to jump to 1.
Can you do like 0 to 1, but like on the y, it will go 0 to 2? Or does it have to go 0, 1, 2 in the y?
One more time.
Like, for example, in the x, it's going to go 0 to 1. But the y will go from 0 to 2. Can you do that or no?
No, we can't skip over the 1.
Oh.
Yes, good question. We cannot skip over this. We need to have these in order. Otherwise, we'll be missing part of our graph. So yeah, it's important that we start with the idea here. Must have all of these. It'd be nice if we can say, I don't like fractions. Let's just scratch that out. If this were just a regular y equals 2x, yeah, it wouldn't matter because we're just going to connect everything in here. This is a little different. So from here, it's going to go only to a half. Open circle, then it's going to jump. Then it's going to go to 1. At 1, right? When you get to 1, it jumps to 2. Jumps up to 2. So at 1, x equals 1. If x equals 1, it jumps to 2. Y equals 2. And then it only goes for a half. And then it jumps again. So you see the steps are very steep on here. And of course, we can go in the backwards and we'll get the same thing. So by a half. So here's a way of looking at it. See this number? How do you know what to count by right here? What's the reciprocal of that number? What's the reciprocal of 2? A half. That's how I know to count by halves. Go back here. What's the reciprocal of 1/3? What's the reciprocal of 1/3? 3 over 1 or just 3? What do we count by? We count it by 3s. So that's how you figure out when there's a number right attached to the x. That's how you want to count when you're doing this. That way you won't skip over anything. If we wanted to say I don't like halves or something like that, if I took that out, this is what would happen.
That's no good.
I'd have something missing. Somewhere between a half and 1, there'd be no answer. There'd be nothing there. So you have gaps. So you got to make sure always it's a function. It has to be a continuous function. All right. Again, the domain. All reals. This is the fancy way of saying reals. It's kind of like an R. So it's like this, but there's like another line straight down. So it's like that. Kind of like that. It's fancy. fancy for all reals. Range integers, same thing. Again, like this. That's fancy. Fancy way of writing all integers. That's what you see in every calculus book and math analysis that gets in next year. You'll see written like this script. Capital letters only. Right, piecewise functions. I know we got a lot, but we got one more little thing. Graph x, graph 1 over 1 x plus 2. What does that look like? 1 over 1. So 1 over 1x, which is 1x plus 2. What does that look like? Y-intercept is positive 2. Start here, up 1 over 1. Now keep in mind this is a regular function. We're not doing step functions anymore. We're doing go back in the day, good old times. There we go. I'm just graphing lines like this. I can do this nicely. There we go. And what about this? How do you graph that line? Well, okay, that's 3 over 1x. There's no y-intercept, right? Start at 0. Up 1 over 3. Down 1. Left. Or down 3. Left 1. I'm just doing rise over 1. And then I can have another graph. And I can have another graph. This is called just graphing two lines on the same graphs. However, the catch is, what makes this piecewise? Okay, so step 1, and I'm going a little fast. Step 1, take these two, whatever they give you, just graph it, all in the same thing. And then, right here, we're going to say, that pink line right here, we only want to have that there for all the x's that are less than or equal to -2. Not the whole thing. We don't want it all over the whole graph. We only want it up to whatever they tell you. X equals -2. That's right here. That's right here.
So the lines aren't in,
Yeah. So I want only the pink graph left of -2. I don't want this part over here. So erase it. Pink graph only go up to -2. And it says I only want it from -2 and to the left, less than -2. Same idea for here. I only want this graph from +2 to the right, greater than -2. So here's -2 again. So I don't want it right here. I don't want it right there. I'm going to move it back. That's piecewise. That's it. Graph everything, and then see where it says, oh, from here to here I want it only. I don't want it all over the place. And you'll never have anything overlapping. Okay? The important thing is just to know that these cannot overlap. So you do not want anything overlapping because, let's say, this blue line, for some reason, went over here instead. Look what happens. Remember, what are we doing? Graphing each function. But if we have overlapping, this will no longer be a function. So you'll never have any of these lines. Doesn't matter what it is up here, nothing overlaps because then it would not be a function. All right, good luck, everybody.